Now we're going to do a two proportion test. We're going to use the same data file as we actually used in the one proportion test. So let's start with that. Just open the OpEx file, two proportion test. As I mentioned before, we've got two tabs here. This tab has the samples in different columns. This one has the samples in one column. What we're looking at here is customer satisfaction data for two areas, area A and area B. So you can see in column one, that's the customer satisfaction for area A. You can see you have satisfied, 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 not satisfied, not down. In area B, you have the results for area B. One thing that's worth noting is for area A, we have 80 surveys in the sample. And for area B, we have 100 surveys in the sample. On the other tab, the samples in one column, what you can see here now is we have all of the survey results in one column. So you have satisfied, satisfied, not satisfied, and you can see it's a total of 180 rows. And then in the adjacent column, column 2, we have the area labels. You can see area A, and then you can see results for area B. So we're going to do the two proportion testing using both versions of this data. The tab I'm on now, where it says samples in one column, this is what we refer to as stacked data. So we've got the results for our two areas arranged in, well, the results are arranged in one column. We have the results for area A stacked on top of the results for area B, and then a separate column labeling which area those are for. We refer to this as stacked data. So the question we've got is there a difference in the proportion of customers satisfied between area A and area B? Of course, our null hypothesis will be there is no difference. The alternate hypothesis would be there is a difference. So I'm going to go to stat, basic statistics, and two proportions. We're doing a two proportion test. The default that comes up, you'll see, is both samples are in one column, which is the way this data is arranged here, this stacked version of data. When I click into the samples column, what it's asking for there are the results. What's the dimension that we're measuring? What's the variable that has the proportion we're measuring? And that's customer satisfied. So that's the output, that's the Y. And our Y is a function of X. The Y is the proportion satisfied or unsatisfied. And then the sample IDs, that's the label for the area. So if Y is a function of X, the proportion satisfied is a function of which area customer is from. Area goes in our sample IDs box. That's where the X is. Y is a function of X. Okay. So we have our results test and confidence interval for two proportions, customer satisfied by area. The event being measured is when the customer satisfied variable equals satisfied. So the proportions being calculated will be the proportion where the customer satisfied variable equals satisfied. So we have P sub 1, and where the area is A, and then P sub 2, proportion sub 2, is the proportion where the customer is satisfied and the area is area B. So it's looking to see whether there is a difference between proportion 1 and proportion 2. Remember, our null hypothesis is that there is no difference. So we have our results here for area A. There were 80 surveys in the sample, 72 were the customer satisfied. That's a sample proportion of 0.9. Area B, there were 100 surveys in the sample, 79 where the result was satisfied. So it's a proportion of 0.79. So we're looking to see whether there was a difference between P sub 1 and P sub 2. If there is no difference, then P sub 1 minus P sub 2 would be 0. Right? If they're the same, then A minus B is 0. So the null hypothesis there is H sub O, P sub 1 minus P sub 2 equals 0. There is no difference. The alternative hypothesis, H sub 1, is that P sub 1 or proportion 1 minus proportion 2 is not equal to 0. There is a difference. So we have two results here. We have the normal approximation with the p-value of 0.37, and we have Fisher's exact with a p-value of 0.065. So the question becomes, which result do we use? Fisher's exact becomes important when the proportions being measured are very large or are very small. So we're looking at proportions of 0.9 or 0.78. If we were looking at proportions that were more like 0.95 or 95% or greater, 95%, 98%, 99%, when those proportions are at the extreme ends, or when those proportions are very small, like 5%, 4%, 3%, and we're trying to determine whether there's a difference in very small proportions, we would use Fisher's exact. Since that's not the case, we do have a high proportion, 0.9, but that's not so large that I would consider it to be very large. In that case, we can use the normal approximation result, and that p-value is 0.037. That p-value is below our alpha threshold of 0.05. P is low, so the null must go. Therefore, we conclude that there is a difference in the proportion of customers satisfied between area A and area B. And we can see that for area A, 90% of customers are satisfied versus area B, 79% of customers are satisfied. Now, we're going to do the same test again, but we're going to use the samples in different columns. This is what we call unstacked data. I'm going to just label these results here so you can see that we're talking about stacked data, and then we'll get another result below that. It'll be the same because the underlying data is basically the same. It's just arranged differently. So to work with unstacked data, where your samples are in different columns, a sample for area A and a sample for area B. Again, we go to stat, basic statistics, to proportions. We click on this box here and choose each sample is in its own column. So it's asking which column is sample A in? Well, that's column C1. Which column is sample 2 in? It's in column C2, that's area B. Click on OK. And so now you can see we're doing the testing confidence interval for two proportions, area A versus area B. The event, again, what's being measured is when the result in the column is satisfied. P sub 1 is for area A. When the result is satisfied, P sub 2 or proportion 2 is for area B, where the result is satisfied. And we're looking to see whether there's a difference in P sub 1 and P sub 2, or proportion 1 and proportion 2. Have the same results, area A, sample of 80, events 72, proportion of 0.9, area B 100 in the sample, 79 events, proportion of 0.79. And again, you can see the difference here, or the results here. And the results here are the same as in the earlier version. Again, the underlying data was the same, it's just being arranged in a different way. I'm going to go ahead and show you a third version of this. Again, if you go to basic statistics, two proportions. And the first thing we did was we looked at where the samples are in one column. Then we looked at where each of the samples in its own column. We can also do this with summarized data. So again, you might not have the raw data. You might just have data being reported to you. So in sample one, I'm going to treat area A as sample one. The number of events was 72. The number of trials for sample one was 80. For sample two, area B, the number of events was 79, and the number of trials was 100. Okay. And again, I get essentially the same results. Because the proportions are not extremely high, I'm using the normal approximation p-value result, 0.037. P is low, the null must go. So I reject the null hypothesis and conclude there is a difference in the proportion of customers satisfied between sample one, sample two, or area A and area two. Area A and area B. I'm going to go ahead and modify these labels so that if I need to refer to it later, I can. So you can see it changes that there. Here. So now in my navigator, I've got the results labeled for the approach that I took to each of those tests.